So with that, let me introduce Skander Hannachi. He is one of the many brilliant Googlers that I'm privileged to work with, and a super nice guy, and loves to discuss technology and share things about it. So I'm excited to have him here in the Google Cloud Advanced Computing community for the first time. Skander, thanks for joining us today.
Thanks, Jay. Good morning, good day, good evening, whichever time zone part of the planet you're in. My name is Skander Hannachi. I'm a technical solution manager with the Vertex AI team, or the Gemini Enterprise Platform team. Currently, I focus on research commercialization and operationalization. So I work directly along with Jay, actually. Jay is also involved in this with the DeepMind team on how to take AI for science models and see whether how do they work in the wild in an industry context, not just in a controlled lab experiment. Prior to Google, I spent around 10 years as a data scientist working on supply chain optimization and demand forecasting. And before that, I was briefly a researcher. I have a PhD. My thesis was on the intersection of quantum computing and machine learning, but that was a long, long time ago. So today, let's talk about how we use AlphaEvolve to optimize code. So this is an outline. We're going to brief TLDR for what AlphaEvolve is, and then we're going to talk about the historical and research context that led us to AlphaEvolve. Then we're going to go back and do a slightly deeper dive on explaining how AlphaEvolve exactly works as an agent. We're going to go through some of the key capabilities, like what are the things where it really shines and kind of like provides new opportunities and not just like incremental improvement on existing tools. And then we're going to, obviously, AlphaEvolve is not perfect yet. There's still some challenges and open questions. And then finally, where do we think this technology is headed? So understanding AlphaEvolve as an agent. So AlphaEvolve at a high level is an agentic loop. It's a fixed loop. It's not one of those autonomous agents that has like different trajectories and anything. It's a fixed repeated loop where you start the loop with a human operator who defines a problem to be solved. And so this problem is obviously a code optimization problem. A little bit more about that later. And then they define what they need to be solved. And they configure a lot of additional details besides just the definition of the problem. And then what happens is the LLM ensemble generates potential solutions. The evaluation pool estimates how well those solutions perform according to the target optimization criteria. Those are stored in a program database. A prompt sampler then looks at the latest generation of programs and generates a new set of candidates, and then creates prompts for the LLM to generate a new set of candidates that hopefully would perform even better than the previous generation. And then rinse and repeat. You go through this cycle for hundreds, sometimes even thousands of times until you get to a program which is net new improvement compared to your initial starting point. Now, what is the evolve about in AlphaEvolve? AlphaEvolve, we have AlphaFold, AlphaGenome, AlphaMisense, etc., which are life sciences related deep learning models. AlphaEvolve, despite the name, is not a life sciences related agent. The evolve comes from a completely different part of the science world, which is mathematical optimization and engineering design optimization, combinatorial optimization approaches. There's several gradient-based methods, rule-based solvers, population-based methods. Within population-based methods, there's a category called evolutionary heuristics. And then within evolutionary heuristics, there's a special type of algorithm called genetic algorithms, which rely on the principle of survival of the fittest. They'll like apply a virtual conversion of the survival of the fittest principle from Darwin's theory to like general purpose optimization problems. And AlphaEvolve is a direct descendant, so to speak, of genetic algorithms, but it adds like an agentic LLM twist to that. So what makes it special? And when for those who are familiar with mathematical optimization and search techniques, their almost immediate reaction is like, come on, we have hundreds of different types of evolutionary and genetic programming approaches. Why do we need just another one? And here, like, if you don't take away anything from this presentation, this is the key kind of piece of information. Yes, it is a descendant of genetic algorithms, but it combines the concepts of how genetic algorithms work with this idea that everything is, instead of being encoded as a gene or as a chromosome. So in genetic algorithms, you take your problem, you have to jump through all sorts of mental hoops to figure out a way to encode it as a gene or as a chromosome, and then apply this artificial um, simulation of survival of the fittest, and then decode it back into the original formulation of the problem. Whereas with AlphaEvolve, you just write it out in Python or C++ or whatever your regular coding, your favorite coding platform is. So effectively, it solves for a major pain point for previous generations of evolutionary and genetic algorithms, which is that it was very hard to encode the problem correctly into a chromosome or into there's other variations like tree-based chromosomes, etc. So in doing so, what happens is it effectively starts bridging the gap between the more pragmatic and somewhat flexible genetic algorithm type approaches to optimization and the more transparent and structure-based methods like simplex, gradient-based methods, etc., which were much more interpretable and transparent, but were very rigid and applicable only to a narrow kind of category of use cases. So what AlphaEvolve really is not so much like, oh, we got a better genetic algorithm. It's more like we're starting to crack the nut on how to reconcile those two approaches to mathematical optimization. And then on top of that, the fact that it uses large language models and relies on, what nowadays we're calling context engineering, I still think of it as prompt engineering, is that you can include semantics. You can also add not just numerical constraints and numerical objectives in your design space, but you can also add additional like meaning-based conditions and lexicographic-based constraints, etc., into your optimization process. And then an additional bonus is that the flexible harness, like AlphaEvolve is a cloud native API that can integrate with just about anything. And so you can essentially use most optimization methods are heavily dependent on the type of objective function. Like if it's, gradient descent by its very name relies heavily on the fact that you can calculate the gradients of your objective function. Surrogate-based methods like Bayesian optimization, etc., rely heavily on the structure of the surrogate function, etc. Whereas with AlphaEvolve, because it's an open harness that can integrate with anything, you can mix and match whatever type of objective function you want, and you can also there are new types of objective functions that are not possible with previous optimization methods, which are now possible with AlphaEvolve. One point, it is a code optimization agent. It is not a coding agent. We'll go a little bit into more detail about that later, but specifically coding agents like Gemini CLI, Anti-Gravity, Claude Code, etc., are interactive, and they're intended for like the general user, the entry-level user, the non-expert user who just wants to get textbook correct code out or who wants to fix buggy code. AlphaEvolve is not that. AlphaEvolve, it's not interactive. It's very much a batch-based, offline, or to use modern jargon, like long horizon type agent. And it's also geared towards the expert user, the power user. So, the user has to be someone who knows very much what they're doing. They have to come up with a program that's like already correct. And it's, to their best of their knowledge, like the kind of best or baseline, good implementation of their problem. And then AlphaEvolve starts there and tries to move the needle on performance by coming up with something net new, something better than whatever the user has seen before, right? So very much geared towards power users and expert, like engineers, designers, operations research scientists, versus like towards, people who are just trying to get textbook correct code out, and that's it. These are like, there's too many to go through in this slide, but these are several of the use cases. On the left-hand side are use cases that have been implemented by different teams at Google, And I apology, like here, I accidentally duplicated this twice. Actually, one of them was quantum computing for molecular geometry. The other one was for fusion devices, not quantum computing. So sorry about that. And then on the right-hand side these are several of the use cases that we have been working on with Google Cloud customers who were piloting the AlphaEvolve API over the last few months, over the last 2 or 3 months. And right now, no longer need to be part of the pilot program. It is, as of last week, publicly available for everyone. Okay, so let's now dive into the context. How did we get to AlphaEvolve, right? So historically, there have been, as you saw earlier, there's multiple ways of performing general purpose mathematical and combinatorial optimization and applying it to various business problems. Supply chain optimization, that's what I did for a decade before Google. Financial, portfolio optimization, various forms of engineering design optimization, very broadly applicable. Economists use optimization tool all the time, as it's one of their key kind of toolkits, etc. But optimizing code was very hard, and specifically, code optimization problems tended to lie very much on the worst case scenario spectrum of optimization. So like very much in the NP-hard non-convex optimization space. Almost all of the optimization methods relied on the structure of the design space in some way or another, either on the, what are the decision variables, what are like the degrees of freedom that you're allowed to go through as part of your optimization problem, or on the shape of the objective function itself. Like I mentioned earlier, can you calculate the gradients, etc. But with a space of possible programs, it's a completely unstructured space. There's no fixed number of dimensions. There's no notion of distance between two programs. Like, is a scikit-learn linear regression closer to a scikit-learn logistic regression, or is it closer to an R linear regression? Like, there's no concept of distance in the space of possible programs in which to anchor like one of the traditional operations research heuristics, which would allow for like a more smooth and interpretable optimization method. And so because of that, the go-to approaches, and if you did a like a code optimization search on Google Scholar, you'll find that most of the methods were either some form of genetic algorithm or some form of reinforcement learning. In both cases, encoding the program the right way for it to be applicable to the model was very hard, and almost always ended up being use case specific, but also encoding the constraints, like taking syntax and grammar rules, all sorts of conditions around, like coding, etc., and then turning those into constraints and penalties for your optimization objective was even harder. So like for example, there were ways, there is a variation on genetic algorithms called genetic programming, where instead of using chromosomes, you use trees. So it was pretty straightforward to encode a program into a tree, but then coming up with a mutation and crossover factor for the genetic programs that respected the grammar rules and constraints was still very, very hard, even if encoding into the tree-based structure was more intuitive than encoding into a chromosome. And what was the result of this? Like the horrible, like looking at it from my practitioner perspective, is that we were sitting on like 3, maybe arguably 4 decades worth of research papers and results, different approaches. None of them turned into a general tool for practitioners. Best case scenario, like the people who did the research, part of an applied team, and they did some optimizations as part of their experiments, which they just baked directly into a C++ library or into their proprietary code base, but there was no kind of reusable tool that came out of this. So with the arrival of large language models, we started seeing a light out of the end of the tunnel, how to get out of this. First, large language models themselves got to a point where we no longer needed to have use case specific language generation. Large language models are perfectly capable of generating C++ or Python or SQL or whatever. So we started getting out of the bottleneck of having the approach be very specific to one programming language and to one use case, and to be generalizable across different programming languages. With Alpha Code, the key innovation there was that we started figuring out how to bring in use the generation. So Alpha Code is under the hood. It's like a variation on the T5 architecture, which is an earlier generation LLM prior to Gemini. So how to combine an LLM with the type of ranking and filtering and sampling that is common to genetic algorithms and to other like gradient-free based optimization methods. It was, strictly speaking, it was not for optimization. It was for competitive programming, but still, competitive meant that it was like meeting a higher bar than just textbook correct code. And then AlphaDev, which was a reinforcement learning model, not a large language model, did show us that a deep learning model could come up with net new. So like in the AlphaDev paper, they have an example where it came up with a net new sorting algorithm. It didn't just come up with the best applicable sorting algorithm, it invented a new one, right? And so from here, the next step was FunSearch, and not just FunSearch, but there were several other models, science models from DeepMind, which followed what I refer to as the validator in the loop pattern. So what's the validator in the loop pattern? The validator in the loop pattern is you get this, you have an agent that, like generates, goes into a deterministic evaluation and testing suite that provides a bunch of scores and detailed feedback, and then loop, and you rinse and iterate. Like I mentioned at the beginning on like how the AlphaEvolve API actually works. This is that was kind of what the this wasn't one just pattern applied to AlphaEvolve. There were several like alpha geometry, alpha proof, etc., where this kind of notion of a validator in the loop, and it is what is referred to more broadly as neurosymbolic AI. So it was a combination essentially of deep learning based or large language model based, so neural network AI, and then on the same hand, it also combined approaches from symbolic AI because it leveraged reasoning and formal methods to do the feedback and the kind of validator in the loop. FunSearch, specifically among these different validator in the loop things, was provided two key innovations. The first was it had a systemic and opinionated but very use case agnostic, so generalizable to any use case evaluation process, whereas alpha geometry was very specific to geometry use cases. FunSearch was completely the opposite, a very flexible, open-ended evaluation process that made it very broadly applicable. And then the focus on functional spaces, so it optimized functions, meant that it can go from optimizing code to being a general purpose mathematical optimization tool, not just a code optimization tool. And then finally, AlphaEvolve was the natural evolution, pun intended, of FunSearch. Specifically, it went from functions to just any algorithm. It went from working just for Python to working for any programming language. And it went from single objective optimization to multi-objective, including Pareto optimal, for those who are familiar with multi-objective optimization. And not listed here, listed here as well. AlphaEvolve also went, FunSearch required a very large number of samples to converge towards an optimal solution. AlphaEvolve required only thousands, and more recently, when we worked with customers on EMP, sometimes just hundreds of samples to converge. Obviously, given the cost of tokens and given just the overall resources leveraged by an LLM, going from millions of samples to thousands of samples is a very, very important criteria. Now, let's go back a little bit and double click on understanding AlphaEvolve. So a coding agent, you have a sorting task, right? A coding agent, you're like, here's a list, I want to sort it. Well, use bubble sort. Don't use a naive approach. Or if you tried a naive approach and it kind of runs out of memory or throws some other execution time error, you'd hand it to the coding agent and it would say, yeah, you're using a naive sort. You should have used bubble sort. With AlphaEvolve, what you do, you wouldn't use it for a textbook problem. You would have a more interesting kind of unique use case And so you have like a custom sort for a very specific use case. You would also provide it with a bunch of functions on how to calculate the metrics that you want to optimize. You want to optimize it for runtime, memory consumption, etc. You also provide it with unit tests to make sure that the new programs that it generates are functionally correct. And then you provide it with a set of test cases for it to run the evals on, right? And so it will spin around. Like I said, it can take hundreds, sometimes thousands of iterations, and it will typically run for several hours or up to a day. And then you come back and finally it will output, here's a new, much more advanced or much more like optimized version of your program for your specific use case, which you wanted to run under 3 hours. It runs in 2 hours and 35 minutes on average, and it consumes on average 8 gigabytes. You wanted it to be under 10 gigabytes, right? Now, a question that comes up often is like, can't a general purpose research agent, like Google's Deep Research Agents or Karpathy's Auto Research or Claude Code, etc., do this on its own? Like if you look at the Auto Research blog post by Karpathy, he says, just tell it what to do and let it go on for a day. No, emphatically no. That would work only for problems that are so-called convex in the optimization world, because those are the types of problems where like just what we call a greedy method in the OR world, in the mathematical search world, where like just try harder, try harder, try harder is guaranteed to converge. But most interesting business operation research optimization problems and code optimization are NP hard, which means they have multiple local optimums. And so a greedy method will converge to one of the local optimums and then get stuck. Now, one might think, yeah, but wouldn't it just it can just try again, right, to get out? Like, how hard is it for it to think, hey, I might be in a local zone, like retry this? Keep in mind that the real world business examples of these are not two-dimensional. This is a two-dimensional space just for visualization purposes. But in a real world optimization problem, you're going to have hundreds or thousands of individual decision variables, or you're going to have a large unstructured embedding space. And so these local minimums, so if you have 100 decision variables, then these local minimums live in a 2 to the power of 100. Like it's an exponential size space, and the number of directions it has to choose from in order to get out of the local minimum is ginormous. And that's why it's impossible for it to kind of just through sheer reasoning alone get out of a local minimum. And hence, general purpose coding agents cannot solve these type of NP hard problems on their own. Here's a concrete example. This was credit to Ivan Nardini from my team who put this example together. He applied auto research and AlphaEvolve to the problem of fine-tuning Gemma 4 on a very specific set of tasks. And in reality, auto research, given the way it works, got stuck, whereas AlphaEvolve is designed to be a population-based method which tries to efficiently sample from across the entire search space, right? More generally, a generic coding or reasoning agent can solve optimization problems for which there's a closed form analytical solution, where you can just directly calculate the optimal solution based on first principles. Or if the problem is so-called convex or convex-ish, concept of convexity doesn't directly apply to programming spaces, but a greedy method is guaranteed to convert. Most interesting problems, whether they're general purpose mathematical optimization or code optimization, lie in the NP-hard non-convex realm, and that's why you need a dedicated optimization heuristic like AlphaEvolve, not just a reasoning agent. Moreover, these are complementary, right? When we work with our customers, we recommend that they use anti-gravity or Claude Code or whatever to prime their program first, to come up with the best possible baseline, and then apply that to AlphaEvolve. And that's why we put together an AlphaEvolve skills file that actually allows you to kind of use a coding agent in order to put together the best possible seed program and the best possible harness before you start running your AlphaEvolve experiment. Now, from here, I would like to go into AlphaEvolve key capabilities. And I want to start here with a personal pet peeve, which is that engineers and scientists, we tend to be extremely empirical and data-driven, and therefore we tend to over-index on benchmarking. And when you over-index on benchmarking, you are missing the forest for the trees. So a lot of people are looking at AlphaEvolve and saying, how does it compare to my existing solver, right? Yes, there are scenarios where it might outperform your existing solvers. There are other scenarios where your existing solver, despite you thinking about it as legacy sometimes means it has 20 or 30 years of accrued tribal wisdom baked into it. You're not going to be able to compete up against that just with one like, hey, AlphaEvolve is better, right? So thinking about how to get incremental performance improvement over existing methods is a useful for like empirical benchmarking. It's missing the forest for the trees in terms of what AlphaEvolve can really do as an agent. And specifically, as I mentioned earlier, it acts as a bridge between different types of optimization approaches, and that's where all of the really interesting, innovative use cases lie. So let's, kind of take a, first in order to explain what's happening on the right side here, like what are these truly innovative use cases? First, we need to kind of double down on what the AlphaEvolve architecture looks like. So the end user has to provide a seed program and add some additional context. They also have to design specific target optimization metrics, and they need, even if it's a single objective optimization use case, we still highly recommend that they put together 3 or 4 metrics because it allows for AlphaEvolve to reason more correctly about the problem space. And then they have to put together the test cases and design the harness. Right now, let's look at the harness. Specifically, an AlphaEvolve harness should have 3 types of tests. The solution validation is for hard constraints, if you're familiar with the concept of constraint and optimization, or like compile time tests from a programming perspective. Solution verification is for like soft constraints in OR terms, and for like functional or runtime tests from a software perspective. And then the solution evaluator is for actually calculating your objective functions themselves. If you're looking at it from a software perspective, it's the solution evaluator is your performance tests or your load tests, right? So again, the first stage is running hard constraints, which treat them as compile time tests. Soft constraints, treat them as runtime tests, and objective functions, which are performance tests. And then finally, you take all of those scores and you combine them into a JSON package, and you also aggregate them to get a, the single or like the Pareto, list of scores that you want to actually hill climb against. Now, what does this, specific, very opinionated, but very flexible architecture mean? If you open a textbook, this is an example of a textbook, Engineering Design Optimization, from Cambridge University Press. Highly recommended. It's a really good book, by the way. The different approaches are always going to be listed in terms of the types of objective function. Can you calculate the gradient? Yes, use gradient descent. You can't observe the gradient, use a direct method. If it's, like black box, again, go use Bayesian optimization. So all of the different approaches are entirely predicated and contingent on what the structure of the design space is and what is the type of optimization objective. Can you observe it? Can you not? Can you calculate the gradients? Can you not? Etc. Right? AlphaEvolve, because of the evaluation structure I just showed earlier, is completely agnostic about those, which means you can combine multiple, and it also allows for new types of objective function, which are not possible before. So I'm going to go into some examples of that. So first, let's take an example where it is combining ideas from like traditional mathematical programming and Bayesian optimization in one place. So this is an anonymized version of a real-world implementation where for a complex engineering design problem with really long and detailed constraints, the constraints were such that any given solution was just as likely to be unfeasible, unacceptable as it was like feasible. And so we couldn't just like do some basic tests and some penalties. You needed to run like do some constraint programming and run like a rigorous logic formal method-based constraint solver. Google's open source CPSAT is very good for that, to test the feasibility of a solution. Then you used a surrogate function because the engineering system was too complicated to calculate the gradients of the objective or to estimate the objective directly the way you would with like traveling salesman or something. So instead, they use the surrogate function, which, there are specialized, TensorFlow probability and Flax tools that are based on JAX to do certain types of surrogate functions. So here you have like, feasibility. Instead of using penalties the way you would with genetic algorithm, you use like rigorous, purely deterministic feasibility tests using Google's OR tools, and then a surrogate function using JAX running on GKE. Now, let's look at a second example. Here we have a traveling salesman problem. You don't need something as heavy-handed as GKE or whatever to calculate the function. But because this is intended for a real-world industry application, instead of doing just the tour length, which is what the textbook, the textbook version of traveling salesman would involve, you want to make sure that the solution runs in a reasonable amount of time. So first, you put a test to make sure that the runtime of a proposed solution is under X amount of minutes. That's a hard constraint. Now, tour validity is also a hard constraint, but you treat it more like a penalty in the way that you do in genetic algorithms than you do like a deterministic hard constraint. Now, average improvement over a random tour, because you're probably going to reuse this solution multiple times, is more like of a stochastic optimization objective, and tour length is a deterministic objective. So here we have two different types of objective functions and two different ways of addressing like feasibility and penalties mixed into the same evaluator. Now, example 3 for IT infrastructure. This is for optimizing like IT infrastructure. You can use surrogate functions, which current Bayesian optimization methods are not compatible with. For those familiar with Bayesian optimization, like the way Bayesian optimization works is you cannot observe the objective function directly, so you build a regression model that predicts the objective function instead. And for Bayesian optimization to work, there has to be some really strong conditions on the type of prediction model, and also like there are limits on how many variables the prediction model can take as input for Bayesian optimization to work. But with AlphaEvolve, you're no longer like constrained by those conditions. If you can use any type of surrogate function or any type of proxy function. So in this case, they used like a highly specialized kind of physics and Monte Carlo Markov chain based simulator, as opposed to using just like a Gaussian process or linear regression or whatever, which would have been the only option for Bayesian optimization to work. Right. So this is a case of AlphaEvolve allowing for a completely net new type of surrogate function that was not possible with previous like Bayesian optimization approach. So as I said, this is a new technology. There's still some challenges and open questions. Our biggest challenge so far has been benchmarking. Benchmarking open AlphaEvolve is really, really hard because on open source optimization benchmarks, the LLM tends to very quickly memorize the state-of-the-art results. So for example, our kind of hello world, this is Jay's quote, not mine. The hello world of AlphaEvolve is a kind of a textbook mathematical optimization problem called circle packing. It does a really good job of illustrating how AlphaEvolve works. So using the V1, so we were still working on the pilot private preview, the V1 of the Cloud API, which used Gemini 2.5, took about 18 hours and 1,000 iterations to converge on our textbook circle packing example. And then for V2, we switched to Gemini 3, and suddenly it took less than an hour on only 4 iterations. Was it because V2 was that much awesomer than V1? No, it was because Gemini 3 training cutoff was after the AlphaEvolve paper was already released, and it had memorized the results from the paper. So it wasn't optimizing. It was just, this is what Alan Turing referred to as an oracle. As part of his analysis of Turing machines and the limits of computers, he had came up with this purely, hypothetical construct. How good would an algorithm be if occasionally it could just ask an oracle for what the correct answer was? Lo and behold, here we are a few decades later, and it was no longer like a hypothetical construct. We actually have LLMs acting as oracle machines as Alan Turing described them. Another thing like that's kind of been an issue is like for regular optimization and mathematical search problems, there are various rule of thumbs. Like when you talk to like a financial services data science team, can you tell me about your optimization use cases? Oh, this way, portfolio optimization for this type of portfolio. Oh, that's quadratic, that's convex, AlphaEvolve is not a fit. What is this? Oh, this one is a portfolio optimization, but with a cardinality constraint and a much more nonlinear objective. Oh, that is a fit for AlphaEvolve. So there's some rules of thumb and accrued tribal wisdom on what problems are convex and what problems are non-convex, which allow you very quickly to scope an AlphaEvolve use case. When it comes to code optimization, though, given, as I mentioned earlier, the concept of convexity is still applicable in spirit, but not applicable directly in its explicit formulation. So there's not those rules of thumb of figuring out when is a code problem something that really requires the full might of AlphaEvolve, and when is it something that like just a regular grid search or Bayesian optimization routine would solve for. Additionally, steerability. We have been having some very vivid animated discussions even internally within our team on how does exploration versus exploitation work in the context of AlphaEvolve. For a lot of the black box methods like Bayesian optimization and genetic programming, there are best practices, established ways of balancing the exploration versus exploitation trade-off. Some of us are on the side of like tweaking the LLM mixture in the LLM ensemble, so using more Flash or more Pro is how you tweak that. Others are like focusing more on the temperature. So this is an open question. How much information should you put into the context has been a moving target. We started out with dump as much information as possible. We're now kind of, and then we went during like the EAP with customers to like, no, actually be very minimalistic, put just only the bare minimum. And now we're going back to actually, no, there might be some scenarios where dumping as much information as possible is still relevant. And then in theory, AlphaEvolve works for any single programming language in the world. In practice, we've tried it on some specialized, it seems to work on some proprietary languages, which is surprising, but maybe their syntax is not that different from like open source languages. It also seems to work on PSpice, whose semantics are not at all those of regular programming languages, but the results are TBD. We're not ready to kind of like declare victory and say it works for those. For esoteric languages, go look up esoteric languages on Wikipedia if you're curious, that use like really weird character sets. Back in my home country of Tunisia, which is in North Africa, there's some discussion of like using the native North African alphabet to create a programming language. Yeah, that one, don't push your luck. No, it won't work. Come on, it's AlphaEvolve, it's not magic. So where are we headed with this? These are not official roadmap features. This is just where our experiments and where our thought processes are. Please don't commit us to like these are actual roadmap features. So first, part of AlphaEvolve is like this, besides the concept of genetic algorithms and evolutionary heuristic, there's also a concept called map-elite islands, which improves the efficiency of the sampling. And map-elite islands came from a paper where they talk about not just optimization, but illumination. The idea of map-elite islands wasn't just to come up with an optimal solution, it was to also illuminate, to take your design space and take it from being like a black box unstructured design space into an illuminated one that you understood. And what we've observed is a lot of teams, both internally at Google and our pilot customers, were already doing this off-label. They were going in and getting insights, not just from the final optimized solution, but across the entire spectrum of programs. If you go to the GDM gallery, you'll see a lot of examples, which include not just the final program, but also what the post-experiment analysis across the entire code base looks like. But there are still some questions like, how can we make this systemic? Like, is there a way of doing this post-experiment analysis that applies to all use cases? So far, we haven't seen that. So far, we've seen it like very much like on a use case by use case basis. And can we generalize it to others? And then the other idea that we have explored and tested internally, but we're not ready yet to kind of commit to like deploying, is besides the program database, also querying additional knowledge sources. So you've run the latest generation of candidates, you've gotten feedback. Now, based on that feedback, go run a query on a relevant on IEEE or on Google Scholar or PubMed or whatever the or the AP physics review letters set of journals, etc., and see if you can get any additional insights based on your latest results. And if you're working in an enterprise context, you can also like plug into your internal enterprise knowledge bases and your own groups like crude tribal wisdom to come up with better prompts, right? So this is another thing that we're exploring, and essentially this is I mentioned like benchmarking like accidental oracles. This is like grabbing that bull by the horn. This is like, okay, now we are going to we want intentional oracles. If there's an opportunity to use an oracle here, please do, but just do so intentionally and systematically, not accidentally, right? By adding a grounding or RAG-like component to the loop. Now with that, here are some QR codes. One leads to our Google Cloud open source repo samples that kind of demonstrate how to use the cloud version of the API. And then the GDM examples gallery has examples of programs that are much more research focused versus, so this one is more industry focused, this is more research focused. And they have several examples of what the initial program was, what the final program was, what the evaluation loop looked like. And in the case of the GDM gallery, they also have like that kind of post analysis illumination type thing as well. And with that, I will hand it back to my great colleague, Jay.
Thank you, Skander. Let's give Skander a round of applause for that. Skander, that was a lot of content. You did a great job. I'm so excited. I can't wait to post this on YouTube so many more people can see it. We do have some questions in Q&A. We don't have too much time, so I'm going to ask them real quickly, and Skander, ask you for short answers on these, and for people to send email to us at gcacc@google.com if they want to follow up. And Gianluca gave us the crab icon on that one. Sorry, Gianluca. Anonymous asks, can you erase AlphaEvolve memory?
Yeah, actually, that's a problem right now. The current version, like the program database disappears once you've done the run, and people don't want that. They want the database to persist, as I mentioned that last slide about like illumination.
So can you address whether that's being worked on, or is that an NDA conversation somebody should contact us about?
I wish it was under NDA, but like pleading the fifth is more cop out here than real NDA.
All right, we'll move on to the next question. Ernani asks, is it true to state that it's like listening to an industry expert talking about past events that seems like they're talking about fringe stuff? I'm not quite sure I understand Ernani's question. Is it true to state that I assume AlphaEvolve, it's like listening to an industry expert talking about past events that seems like they're talking about fringe stuff? They just reword things in a way others can better understand, but the reality is that the knowledge was already there. So I think the question rephrased is, AlphaEvolve mostly benefiting from past expert knowledge and finding that past expertise, or is it really finding truly new knowledge? And if so, is it just fringe stuff, or can it derive fundamentally new knowledge? I think that's the rephrasing of that.
That is a
thumbs up if I got that right, Ernani.
Well, okay.
Give me a thumbs down if I got it wrong, Ernani. Oh, I got it right. He says in chat, I got it right.
So that is an absolutely spot on question. And the answer is, it's going to depend on what are you using AlphaEvolve for. Let me give you an example, a concrete example. Like, you want to use AlphaEvolve to improve the fast Fourier transform. Now, for some reason, the majority of the scientific computing community and like signal processing community is not aware of the fact that in 2009, the quantum computing group, so physicists, not signal processing people or math people, physicists, stumbled upon the fact that the quantum Fourier transform, which runs in n log n instead of n or n squared. I forgot what the current FFT is, either n or FFT I think is n squared. The quantum Fourier transform runs faster in n log n. The physicists accidentally stumbled on the fact that you can simulate the quantum Fourier transform completely on a classical computer. You don't actually need a quantum computer. If you formulate it the way the quantum computing crowd does in terms of quantum operators and qubits, you can simulate it perfectly on a classical computer. So they effectively arrived at a version of the FFT that was n log n, not n squared, in terms of worst case complexity. Now, the majority of the signal processing community is not aware of that, right? AlphaEvolve, if you ask AlphaEvolve to improve the FFT, it would accidentally stumble on that result and might apply that approach, right? Now, if you're a practitioner who's just looking for a faster version of the FFT and you weren't aware of that result, great. AlphaEvolve did its job and then some. So it was using existing knowledge. It didn't really invent a new algorithm. But in terms of like optimizing my business problem, perfect, right? I don't need to go read every single paper about the FFT from whenever Joseph Fourier was in the 18th century until the present now. AlphaEvolve I can offload some of that to AlphaEvolve. Now, on the other hand, if you're using it for research, that's not a good result at all, because you want to discover a net new thing. And in practice, it boils down to like the steerability question that I mentioned earlier. And usually, if you want to discover something that's absolutely completely net new, you want your heuristic to run for the thousands of iterations or more, and you might want to rerun it 3 or 4 different times and do that at post-run analysis to see what it's doing before you finally get to a run that gives you something net new. Whereas, again, practitioner, on the other hand, great. If it takes 100 iterations and it stumbles on somebody that somebody else discovered, that's good. I'm not trying to publish new papers. But that is a great question, and it has been a major puzzle for a lot of our users as well.
I learned that lesson from Skander early on when I didn't know much about AlphaEvolve, and I said, Skander, I want to test this out. I want to give it the insertion sort algorithm and see if it derives quicksort. And Skander said, well, Jay, that's not a very fair test, because quicksort is in all the literature and it's been trained on a model that knows about that. So that's not a derivation, really. That's finding a better algorithm than insertion sort. But Skander, I liked your much more complete and comprehensive and detailed answer here as to the limitations here. We have time for one more question, but we have many more questions in the queue, which is a great sign that people were listening and are interested. So I think, Mary, what we need to do is collect the questions in the Q&A here and start an asynchronous capability to have Skander and or Gemini. Is it Skander or is it Gemini? Answer some of these questions in a way that we make available after the sessions, because the good news is this community is getting bigger. More people are coming. More people are asking more questions. And we want to get all these questions answered. We are a community of practice. So, Mary, let's see if we can figure that out and work with Skander to get some answers to the questions we don't have time for. We'll ask one more here, and it's from Lucas Secco, who I had the pleasure of meeting last week. How does AlphaEvolve prevent against overfitting of the code base being optimized? I guess that would look like over-engineered code that won't generalize beyond the unit tests and metrics in your objective function. Please correct me if I'm wrong.
So the concept of overfitting doesn't translate directly to an optimization problem in the optimization world. It was probably its closest equivalent would be getting stuck in a local minimum. Or actually two concepts. One which is specific to like optimization, one that applies to all optimizations, which is getting stuck in a local minimum. And AlphaEvolve uses the map elites concept that I mentioned earlier to create different islands of possible solutions and ensure some diversity in the candidates, which means that it's spread across the search space, and that's what allows it to jump out. To my earlier point about this is why you need something like AlphaEvolve and not just like a general purpose reasoning agent. So it uses the diversity, dedicated sampling and intentional diversity of candidate solutions in order to avoid being stuck in a local minimum. Now, the second type of concept that might be equivalent to overfitting is what we call reward hacking. So reward hacking is when it discovers that, like there's 3 or 4 optimization objectives, but there's only one of them. And if you just focus on that and ignore all the others, you can greatly increase the overall score, which is it's incentivized to do, but you're not really solving the business problem. An example of that is like when we tried this on traveling salesmen, it noticed that if it dropped 2 or 3 nodes, 2 or 3 cities from the tour, it could greatly increase, the optimality of the solutions that it was producing. And when that happens, then what you do is like you observe that you have to monitor your experiment, notice that it's kind of reward hacking, and then once the experiment is run, you go back, and then what we do is like you go in and you either tweak your metrics. You have to tweak your metrics. That's not an either. You tweak your metrics. You might also go into the context and actually spell it out in plain language, like please stop doing this. Right? We've done that with a customer where they actually said, please stop reward hacking by dropping cities from the tour. And that led to it no longer reward hacking, right? Does that answer the question, Luca?
Yes, he says, yes, thank you. And with that, let's put up our final slides real quick, Mary. We've got about 1 minute to share a bunch of upcoming stuff with you.